For decades, the scientific community has speculated about the possibility of life beyond Earth. While this idea once existed solely within the realms of science fiction and philosophical debate, recent advancements in observational technology have shifted this discussion into the domain of data-driven research. With the deployment of the James Webb Space Telescope, JWST, humanity now possesses the most advanced tool ever constructed for the purpose of exploring the distant corners of the universe. Its contributions are beginning to reshape our understanding of the cosmos. The JWST was launched with the objective of observing the earliest galaxies, examining stellar nurseries, and characterizing the atmospheres of exoplanets with unprecedented precision. Among its most compelling recent findings is the detection of potential biosignatures on Proxima b, an exoplanet orbiting the red dwarf star Proxima Centauri, located approximately 4.2 light-years from Earth. The implications of this discovery are significant. For the first time, researchers have observational evidence suggesting that the necessary conditions for life might not be unique to Earth. The technological capabilities of JWST surpass its predecessors in several critical areas. Its 6.5-meter primary mirror is more than twice the size of the Hubble Space Telescope's mirror, allowing it to collect significantly more light and resolve finer details from distant astronomical sources. This capability is essential for studying faint objects such as remote exoplanets and the earliest galaxies in the universe. Additionally, JWST operates primarily in the infrared spectrum, a feature that allows it to peer through cosmic dust clouds that obscure optical telescopes. One of the key instruments aboard the JWST is the Near-Infrared Camera, NIR-CAM. This tool captures images in the near-infrared range of the electromagnetic spectrum, allowing astronomers to study stellar formation, early galaxy development, and the characteristics of exoplanets. The data collected from NIR-CAM are instrumental in analyzing light that has traveled billions of years across space, providing insights into cosmic events that occurred shortly after the Big Bang. Another vital component of JWST is the Near-Infrared Spectrograph, NIR-SPECT. This device performs spectroscopy on light from celestial sources, separating it into individual wavelengths. This technique allows scientists to determine the chemical composition, temperature, motion, and physical conditions of astronomical objects. Spectroscopic analysis is fundamental in the search for extraterrestrial life because it enables the detection of atmospheric components like oxygen, methane, carbon dioxide, and water vapor, molecules typically associated with biological processes. The mid-infrared instrument, MIRI, extends JWST's capabilities further into the mid-infrared range. This instrument is particularly useful for examining cooler objects in space, including newly forming stars, protoplanetary disks, and exoplanets. MIRI is critical in identifying thermal emissions from exoplanetary atmospheres, which can provide evidence of greenhouse gases and other molecules linked to biological activity. One of JWST's most notable targets in the context of astrobiology is Proxima b. This planet, which resides in the habitable zone of its star, has long been considered a candidate for hosting life. The habitable zone is the region around a star where temperatures are suitable for liquid water to exist on a planet's surface. Spectroscopic analysis of Proxima b using JWST's instruments has revealed atmospheric signatures that include traces of carbon dioxide, water vapor, and potentially methane. These compounds, especially when found together, could indicate the presence of biological processes. The observations of Proxima b have yielded data that show distinct absorption features in its transmission spectrum. These features suggest the presence of a stable atmosphere capable of supporting complex chemistry. While abiotic processes can also produce some of these molecules, their simultaneous presence increases the likelihood of biological origin. This is not definitive proof of life, but it represents one of the most promising leads in the search for extraterrestrial biology. In addition to atmospheric composition, JWST's observations have provided insights into the thermal profile of Proxima b. The planet appears to have regions of moderated temperature that could theoretically support stable liquid water. Infrared data indicates that the planet is not subject to extreme heat fluctuations, which supports the idea that its atmosphere may help regulate temperature, a key requirement for sustaining life. Another important factor is the presence of photochemical hazes and clouds in the atmosphere. These features can provide further clues about atmospheric dynamics and the planet's ability to retain heat. JUIC's data suggest that Proxima b may exhibit cloud patterns similar to those on Earth, though further observations are required to confirm these interpretations. Beyond Proxima b, JWST has begun cataloging and characterizing a range of exoplanets with potential for habitability. These include super-Earths, sub-Neptunes, and Earth-like planets orbiting within the habitable zones of their respective stars. Each candidate is studied using transit spectroscopy and direct imaging, depending on the distance and brightness of the host star. The process of detecting biosignatures relies on analyzing how light interacts with a planet's atmosphere during a transit event. When a planet passes in front of its host star, a small portion of starlight filters through the atmosphere and reaches the telescope. This light carries information about the gases present, as different molecules absorb light at specific wavelengths. By comparing these spectral fingerprints to known chemical profiles, researchers can identify the atmospheric components and infer potential biological activity. JWST also plays a critical role in measuring planetary albedo, the reflectivity of a planet's surface and atmosphere. This helps determine surface composition, cloud coverage, and energy balance. Low albedo might indicate dark, rocky surfaces, while high albedo may suggest ice, clouds, or reflective oceans. These properties further influence assessments of planetary habitability. A key goal of JWST is not merely the identification of habitable planets, but the detection of life itself, through what are called biosignature gases. These include oxygen, O, ozone, O, methane, CH, and nitrous oxide, NO. The simultaneous detection of multiple biosignature gases in chemical disequilibrium, particularly combinations that cannot be easily explained by geologic or photochemical processes, would provide the strongest evidence yet for biological activity. In the case of Proxima b, the James Webb Telescope has recorded a tentative but consistent pattern of data pointing towards such a disequilibrium. While the findings remain subject to further verification, the presence of these atmospheric characteristics makes Proxima b a prime candidate for continued observation and study. The implications of this potential discovery extend beyond scientific curiosity. The confirmation of life beyond Earth would reshape disciplines ranging from biology and philosophy to theology and international policy. It would redefine humanity's understanding of its place in the cosmos and raise profound questions about the nature, distribution, and evolution of life throughout the universe. From a technological standpoint, JWST's success underscores the value of long-term investment in scientific infrastructure. Its findings have already begun to surpass expectations, offering insights into phenomena once considered beyond the reach of human observation. As additional data are collected and analyzed, it is expected that JWST will continue to reveal new information about planetary systems, stellar evolution, and the conditions necessary for life. While Proxima b may be the first exoplanet to show such promising signs, it is unlikely to be the last. The universe is vast, and JWST's capabilities are only beginning to be fully utilized. With hundreds of candidate planets awaiting detailed observation, the coming years may yield further revelations that deepen our understanding of the universe and our potential role within it. The James Webb Space Telescope stands not just as a scientific instrument, but as a symbol of human curiosity and our relentless pursuit of knowledge. The search for life beyond Earth is one of the most compelling scientific endeavors of our time, and JWST is at the forefront of that search.